Hey, thank you. So I will thank you for our thank you for the nice invitations, and also thank you for your time to listen for this. And I'm going to switch a little bit more about the topic. I'm talking to a more material side. Today, I'm going to discuss the magnesium alloys, and just to show you how we've been aiming to, how we're going to changing this microstructure, actually the nanostructure, so that we can improve the mechanical property of these alloys. So I'm Guozhen, and I'm from the University of Manitoba. And just in case you have more questions after the sections, here is my email. You can reach out me through that email account. Right. So my presentation will have following content. The first, I'm going to talking a little bit more about the problem, give you a little more about the background and what has been done and what's going on. And then I will discuss the result from my group into two scenarios. The first one is about the nanoscale grains, and then just to show you how we can model the grains deformations and in situ. And then the next will go to discuss the special nanoscale, the structures inside the alloys. So we call it nanofiber. We see in second, it kind of like a segregation at the dislocation array, and then in that way, so we will be able to changing the property of the magnesium alloys, and then we'll reach to the conclusion part. All right. So just to those who didn't know, that magnesium is actually the lightest structure alloys, and it's about 1/3 of the steel and 2/3 of the aluminum. So because of the lightweight, it has been applied a lot, intentionally in the automatic and aerospace applications. But it has a big problems about its mechanical properties, which is still compared poor, and that way it's limited its applications. And on the other hand, magnesium is also the richest element, which means if we can utilize the magnesium, we will be able to have a bunch more materials to deal with there, that we never run out of this. So that's another attracting point. Besides that, it also has been using in the electronic applications. Just in case you haven't know or you didn't notice, some of your laptops and your shell of your cameras are actually make by the magnesium. That's because it also have a very good castabilities, so that we can casting these materials not by the highway plastic deformations for the Euro compression or the standard forming procedures. So again, with all these advantages, it's still having a problem that the magnesium is still suffering compare low strength and poor formabilities. And if we can solving that problem, so we can actually bring these alloys to the big market. So then, let's see. My screen didn't working. Oh, yes. Okay. So the poor mechanical property is actually coming from its lattice structure. We go a little bit deeper in the material size, but if you look at the lattice structure, which I tried drawing here, it maintains what's so-called the HCP lattice. That is a hexagonal close-packed lattice. Such lattice has a different response, which is anisotropy, that is very different from the lattice of cubic lattice, for example, aluminum and steel. And because of that, if you can see here, that we can easily induce the deformations through what's so-called basal slip, which only give you the deformations that is parallel to these planes. And then for the rest of other slip systems, that's a modular deformation mode in materials. We kind of have to give you to apply a much larger forces. It can't be about 100 times difference. So because of that, while we deformate materials, it kind of leading to the anisotropic response. Most of the deformations would go in parallel to the basal planes, not in the other directions. And then with the deformation proceed, you can see that it will be likely leading to the crack and then eventually break the materials. So that will make the poor ductility of such materials. And to accompany like solving, not say solving, but to accompany this problem, what they may have is that for these alloys, they may also induce what's so-called the twinning, another deformation mode. And then in that way, it will introduce what's so-called texture, and then that kind of get the anisotropic response even worse. So in a sense, because the nature of the lattice structures, and then we have to deal with what the so-called anisotropic mechanical response, and the goal is just to turn in the possible or relative activities of all these different different deformation mode. For example, basal slip and non-basal slip and the twinnings. So what people can do, the first strategy is just to reduce the grain size. This applied in both pure metals and also alloys. So here is just a quick like chart to show you what happens if we reduce the size of grains in pure magnesium. So the left is the calculated related activities of different deformation mode. As we're showing here is the basal slip, which we call the easiest slip. You can see it kind of getting like the activities were getting a little bit harder with we reduced the grain size. So that scale bar is showing how the grain size looks like. It's ranging from 100 micron to about 500 nanometer. And if we look at other slip systems, what we call the prismatic slip, here is the grain lines. You can see at the larger grains is about at least 50 times difference. But if we go to the really fine grains here, and it's rather like a same values about 300 and 330, that difference. So in the ways, in principle, if we reduce the grain size, we will be able to bring the relative activity of all the slip systems will be getting closer. And also the twinnings will go with slightly different curves, but the same rules here, but that will in principle give us a better strengthening, because we make the movement of the slip systems a little bit harder, and also make their values a little bit closer. So we can see that from the yield strength, that's one of these applicable values to indicate the strength of materials. You can see while in the region 3, it actually the fine grain range, it's not reduced too much. It's still acceptable. It's better than the coarse grains region 1 here, and it getting the maximum peaks, while we have a kind of a suitable grain size about 1 micron for the pure magnesium. And another important parameters is ductilities, which we can represent by the elongations here, where you can see there with reduced grain size, the ductilities are actually increased dramatically. So that will be the goals. So to the sense that we want to reduce the grain size to the nanoscale range, and then in that way, so we will be able to bring the property of the materials to the scale we want to see. From the chart, is one more thing to notice is the red curves, which is the grain boundary like deformations. That's a different deformation mode because they exist of the grain boundaries. And you can see with reduced grain size, the grain boundary induced deformations has increased and become more easier compared to the rest deformation mode. So there's raising the first question we're going to show you later is that how we can evaluate this different deformation mode while the deformation proceeds. And that's for the like strategy to changing the grain size. And another way is that if we can induce the foreign element, which we call it alloy per size, And then we will be able to induce the anisotropic precipitations within such systems. And by doing so, if we can make these precipitation shapes has anisotropic shapes, and in principle, it will be changing the mechanical response differently. Differently, I mean in the different crystallographic directions. So the left diagrams was just to illustrate the principle, which we select 2 different type of these precipitations, which you can think as another phases inside the materials. And the first one is also called the basal plate. That will be the plate shape of precipitations lying on the basal plane. And another what we call the chromatic plate, it will be a plate that vertical to the basal plane. And if you look at how this increased in the strength to activate this deformation mode, we can see the chromatic plate actually increased dramatically compared to the basal plate. So to change it to the common language, that is, if we want to induce the precipitations, and we want the precipitations vertical to the basal planes, so that it will change more or it will strengthen more about the basal deformations. In that case, we may make the materials a little bit stronger and tougher. How we can do that? So the first ways is that we can select the target element. For example, in magnesium e-tron alloys, and this type of alloys is likely to form in also called this like a chromatic plate. So here is just the illustration to show you we actually view along the c-axis, and that's how the plate will be looks like. But rare earth is a very expensive element, and in principle we can't make a lot of that type of alloys. So then there's other ways we can utilize the grain boundary, like some of these grain boundaries, because it's defective structures, and then it will become the preferential nucleation site for the precipitations. And you can see we can form in this kind of network, but also this chromatic plate like vertical to the basal planes. So that's one of other ways to deal with the situations. And then they're just quite very limited applications if we can only using these grain boundaries, because it has to be the grain boundaries that along the basal planes and has to have this unique structure there. So is there any other possibilities? So here is one of the publications about the inside the ferric alloys, the iron alloys. It's not in magnesium, but it's showing a good possibilities there. So the key idea is that we may have a lot of dislocations that can be likely induced during deformations, and those foreign element, they will prefer to stay with the dislocation cross, which is likely to be more like lower integers for the segregations, and then that structures is not going to have a new phase, but rather than so-called the confined the chemical and the structure state. All in the more common terms, it's just the segregations, and those segregations is comparable stable over medium temperature like heatings in this case, and in that ways we may be able to induce the anisotropic precipitation, not precipitation, but the strength units in the materials, and so that we can turn the mechanical properties of the magnesium. And these things is just not too far from the fundamental science we've been start. If you go back to the heterogeneous nucleation at dislocations, for some conditions, if we have the proper the interface integers, that's the segregation and the matrix interface, and the proper dislocation nucleation like integers, and then in certain conditions we will be able to form in this like the barriers, so that we will form in this segregate at the nanoscale, and then that won't go up because won't grow up. It's because the integer barrier to cross. And so if we apply the principle in magnesium, we will be able to, or we're supposed to be find some like dislocation based strain unit, so that we can turn the property of the magnesiums. So here comes with some result. After we know this background, the result will be quite easy to go through with. For the deformation, like for the deformation mode in the nanograins, the current challenging is that we won't be able to know the orientations changing, or not very limited informations about that, so that we wouldn't know how the grain boundary contributions compare to the dislocation contributions. So it's not the easy to solve problems. It has been seeking for a decade in the like in this field. But what we try to say is that if we forgot about to obtain the whole orientation of magnesium, just focusing on the key informations, for example, how the slip planes, which was the key like crystallographic element, so that we can see how the dislocation proceeds. And if we just focus on these particular crystallographic informations, we will be able to take in like the reciprocal signals that only represent these key crystal planes, and use that ways to do the imaging there. And in that situations, we will be able to see how the orientations will change during deformations. And by doing imagings, we can see those line features was illustrated here. And that's because of the exist of the slip systems, that's the dislocations. So that by doing that, we can did both the dislocation movement as well as the grain orientations together. So here it's just a graph showing you the obtained imagings as well as how the contrast changing with different orientations. So here is the result we've been having now. So you can see with the force applied to the specimen, and then we will be able to see the changing, the contrast changing of the local like grains, which is about the 100 nanometers in size. And you can see some of them become darker and some of them become brighter. It's just because the orientations was, the grains was rotating, or the specimen was like a little bit bending during that way, so that's induced this contrast difference. And the most intensively plastic deformations are actually at the tip front, so that's most forces would add on. And the interesting thing is that we can see the lining features which represent the dislocation activities there, and then the bright grains which showing that all those slip planes which we were targeting at was adjacent or aligned to like to the vertical directions to the planes, and then they actually linking together to forming a kind of pattern. So from the videos, what we can conclude is that I think we should let it finish so that we can go to the next. So it's now it's just the unloading process. So so what we can see is that we can have more bright grains, that we can have more systems that will be vertical to the directions because the applied forces is along the planes. And then we can have the bright grains is connecting, that's showing they try to cooperate with each other. So we also did the post characterization of these structures. So we'll show the evidence of the same things. The grains has been rotated. You can see here is the one orientations before deformations, and here is the orientations after deformations. Actually, we were seeing like our view is parallel to these planes and rotate to the to one of these particular directions. And we can also see the dislocation activities by drawing the box vectors there. So comparing the before and after imaging, so we're also showing you more age-on sleep systems and more age-on planes across the grain boundaries. And here is another movie frame to tracking one particular grains, just to see how the dislocations move through the grains. And you can see they also have this, one of the sleep systems was, one of the sleep planes was age-on, it wasn't changing much during deformations. And then the grain boundaries actually has much less move if the side of the grains they all have the cross like sleep system to the passing through the grain boundaries. So that's suppose the ideas that the alignment of the sleep system, which is corresponding to the dislocations, and then these two different deformation modes are cooperated, and then eventually give you the final property of your materials. So if we jump into the next one to have a little bit fun to see how we can induce the anisotropic nanoscale strengthening unit by dislocations. So the first thing you may thought, how we can bring the solute into the dislocations to the system. So here we select another system of magnesium gadolinium alloys, and of course we need to we need a certain bit certain concentrations. Here we have 1 weight% of the gadolinium. It's really lies about the 0.1 atomic weight% of the gadolinium in the matrix. But if we have the dislocation there, around dislocations, it will have the so-called the stress. So it will give you the compressed stress regions and tension stress regions. And because gadolinium are a little bit larger in size compared to the magnesium, and then those gadolinium are preferable to this tension areas, so that it will have a less lattice distortions induced by the by sitting in the lattice, and such strength will become stronger if we can see we parallel the dislocations in the rays, and that likely the configurations at the grain boundaries. So here just showing you experimentally what we can see there. And if we think a little bit more, to not only focusing on the grain boundaries, because we can have these regular patterns of the dislocations, and then we can induce the next array of the dislocations, and that's with this so-called positive and negative signs, and then there's interactions that the stress fields will become more like the energies will become minimalized, and then the force applied to each dislocations can be less than what less than the force need to induce the movement of that, and in that way we can have this stable dislocation configurations. And if we can also put the segregation on that, it's supposed to give us the target like structures we were looking for. So here is the experimental result in pure magnesium. We can see the patterns if we looking through this like along the c-axis, and those diffractions also represent the patterns, the hexagonal patterns we were seeing here. And then if we change our views to the perpendicular directions, here is along the perpendicular direction here, and then we can see this dislocation arrays. Here is just a magnificent images over here, and that's compare the experimental result of the dislocation curves and with the simulations. So by doing the simple Hall deformations, we'll be able to do that. And it has a little bit difference compared to all reported the dislocation arrays, because in this case, it's not only they are not stayed in the easy sleep planes, that's the C planes. The reason is that we are not only goes through the self-assembling of the dislocations, but also through the dislocations decomposite, and then the cancel with negative sign of one of this the segment, and eventually just leave this C dislocations, which was likely immobile in that situations. So next thing will be how we're going to edit the segregations in that case. So here we back to the alloy systems, and then we bring the dislocation patterns, the lattice there. And then if we imagine how it looks like, Here is the graphs showing you the segregations in the dislocation cause. And this graph is Z contrast images, which means all the bright dots are attracted to the gadolinium there. And then if we tilted the view directions vertically, we'll be able to see how the so-called nanofibers will along that directions. So in conclusions, we'll be able to find the nanofibers as expected. And here is just more graphs to showing you the different patterns exist inside the materials. And how we did that, we do the Hall deformations to induce the enough dislocations, and then we do the quick annealing process so that we can still give you like the segregations or accelerate the segregations to forming the structure we've been targeting at. So in conclusions, the key to advanced magnesium alloys is not only strengthening it, but also turning the relative activity of different modes. There's basically 2 routes to do that with reduced grain size, and there's a lot we have to discuss about its deformation physics, or we can induce the anisotropic precipitations of the strengthening units so that we will be able to achieve the goals as well. So in the last, I think I will skip these ones. I would like to thank my collaborators and group members working on this project, also the founding agent to support my work. So thank you for your attention. I think I need to skip that.
Thank you, Dr. for your unique perspective. Sure. Let me see. We don't have a question, and thank you. No, we have a question.
I think I saw one. Yeah.
Okay. Should I read it?
I can read it. Thank you. So the question is, what is the nanoscale characterization of sharing shared beta precipitations in the deformation aluminum magnesium silicon alloy? I think you guys are really from the material side. Normally when people do that, they usually using the transmission electron microscope so that you can put the post-deformation alloys inside your electron microscope, and then just using different imaging techniques to see how your precipitations will be looks like in that situations. The in situ characterization, which I means if we want to see how the like precipitations was deformed during the microscope, is a little bit challenging, but with careful designs, you may be able to see like all these details there. Usually when you go with in situ testings, it will have to like you have to sacrifice a little bit about your spatial resolutions. It just because the microscope won't be that stable in that case. Did that answer your questions?
Thanks, I think.
Thank you.